Hello, I welcome you all in this presentation. In this presentation, basically, I will be talking about the importance of the grain structure and the methods for quantification of the grain size. The main objectives of the presentation is to understand the importance of the grain structure on the performance of the metallic components and the weld joints in general. Also to learn the methods of quantification of the various parameters of the grain structure, which includes like grain size measured in terms of like the grain diameter or the length or the secondary dendrite arm spacing, the shape of the grains in form of form factor and aspect ratio, and the distribution of the grains in terms of the size and shape variation. And therefore it becomes important to quantify the grain size of the micro structure. So as I have said, the grain structure is important, and it affects the mechanical properties, tribological properties, and the corrosion properties of the metallic components and the weld joints. Also, if the grain structure is fine and it is uniformly distributed, in general it will result in the good combination of the mechanical and tribological properties. How the grain size will be measured, that will depend upon the type of the grains. Like the equexed grains are measured primarily, like say the grain is of this shape, so it will have some area. So to quantify this kind of the grain, what we do, the average grain diameter is used as a parameter, average grain diameter. So how that is determined, basically A is equal to pi by 4 d square. So A, if the A is known, like say A is of the irregular shape, not necessarily circular shape, but its equivalent diameter can be quantified from the like say 4A by pi square root equal to d. So this will be giving us the d equal to the square root of 4a by pi. So this gives us the average grain diameter. Similarly, if we have the needle shape structure, then it is generally the length is the parameter of the needle, which is used to quantify its size. And in case of the dendritic grains like this, so the secondary dendrite arm spacing, like these are the secondary dendritic arms, and spacing between that is used to quantify the SDAS or secondary dendrite arm spacing to quantify the grain size. So the grain size of the dendritic structures is quantified in terms of the secondary dendrite arm spacing. As I've said, in general, the fine grain structure improves the mechanical properties. So if the grain structure is fine, the high hardness, good strength, good toughness, and the high ductility is observed. Classical equation showing the relationship between the yield strength and the grain size, and according to that, the yield strength is found inversely proportional to the square root of the diameter. So finer the diameter, greater will be the yield strength. Therefore, efforts are always made to have the finer grain size in the components. So since the grain size is important, so how to quantify, what are the various methods to quantify the grain size? So there are various parameters. As you can see, the average grain diameter I have explained in the previous slide. Then the average grain area, if there are many grains, few are small, few are large, so the area of all grains are measured, and then average grain area is identified. Then in a particular area, how many grains are there, that number of grains per unit area, like they are just like this 1 2 3 grains, or there are many hundreds of the grains in the same area. So per unit area, how many grains are there, that is the another parameter. Then average intercept length, like say what we do, there are number of grains like this. So we draw one line of the standard length and try to count how many number of the grains are being intersected by this line. So simply we draw one straight line and we see the number of intercepts by the grains or the grain boundaries. So average number of the grains intercepted by a line of the fixed length, the average number of the grains per unit volume, or the average grain volume, are the other parameters which are used to quantify the grain size. So as far as the methods are concerned, there are various methods. Like one is the comparison method, where in one standard chart is used to compare the grain structure of a particular microstructure to identify the grain size. This is largely a qualitative method because it is based on the comparison, not exactly based on the measurement. It's a visual comparison based method. The another method is the planimetric method, in which the average number of grains per unit area is identified, and in intercept method, average intercept length is identified, and in all these cases the grain size is expressed using the ASTM number, which indicates the grain size of a microstructure. So as I have said, according to the ASTM, the grain size is commonly expressed using the simple equation, that is n equal to the 2 raised to the power g minus 1. So here n is the number of the grains per square inch, g is the ASTM grain size number. So basically we try to determine the value of the g using the number of grains per unit area. So when the different methods are used, we use the different equations to calculate the value of g, so that the ASTM grain size number can be identified. As far as the shape is concerned, the grains are found in the different shapes, which may be simply in form of the planar structure, planar grains like this. These may be in form of cellular grains like this. These may be in form of the dendritic. There may be dendritic grains or equaxed grains. These are the four simple type of grains. Other than this, there are like the star shaped grains, then Chinese script grains like this, then simple needle shaped grains or plate shaped grains, flakes are there. So various grains are found in the different shapes. So to quantify the shape, we use the various parameters, and the common parameter like the form factor, aspect ratio, circularity, and sphericity. So the form factor and aspect ratio are calculated using the length to the width ratio, and this factor is important because the shape of the grain affects the stress concentration. Like we can say the particle and the matrix. Like in a microstructure, there are various constraints. So if the particles are of the circular shape, stress concentration at the particle matrix interface will be minimum. But if it is of the needle shape or of the high aspect ratio, in such cases stress concentration at the particle matrix interface becomes too high, and that in turn increases the crack nucleation, and the fracture tendency. Grains of the high aspect ratio results in the lower ductility and the greater fracture tendency. Obviously, the high aspect ratio grains will have the low circularity. Similarly, if the aspect ratio is close to 1 or circularity is close to 1, that is in case of like the grains having the circular cross section, in that case we in general get the higher strength, ductility, toughness, and the fracture toughness, primarily because the stress concentration at the particle matrix interface is found to be minimum. As far as the weld joints are concerned, we can find the four types of the grains, like the planar one, cellular, columnar dendritic, and the equaxed dendritic. So we have to use the different parameters for quantifying the size. Say thickness of this layer will be used in case of the planar structure, then intercellular spacing will be used in case of the cellular structure, and secondary dendrite arm spacing will be used in case of the dendritic structure. So how the size will be measured, that will depend upon the type of the grain which is being considered. The size distribution of the grains can also vary significantly, and that change in the metallic component is primarily observed due to the difference in the thermomechanical histories experienced by them during the manufacturing processes. For example, the welding, casting, and forming leads to a lot of difference in the thermomechanical histories experienced by the metals during the processing, and that is why we get a lot of variation in the size as well as the shape. We can see, as we have seen, right from the fusion boundary to the center, a lot of variation in the grain size is observed. Usually we get the fine grain size at the weld center and the coarser grain size near the fusion boundary. Similarly, here we can see the fine equaxed grains at the skin of the cast components, then the columnar dendritic grains, then the equaxed grains at the center. So large equaxed grains at the center, small equaxed grains at the skin or at the surface of the cast component, and these differences are primarily observed due to the difference in the kind of the thermal cycles experienced during the welding, the cooling rate experienced by the component during the casting, or the kind of deformation and strain experienced by the components being produced by the forming, rolling, forging processes. And so the image analysis help in studying the shape of the grains very effectively. But as far as the size is concerned, size also can be determined using the image analysis, but there are certain very traditional and classical methods for determining the size of the grains. About that we'll be talking this method. So the first method, which quantitatively gives the value of the grain size, ASTM grain size number, is the planimetric method. In this method, the number of grains per unit area is identified, and that number of the grains NA is quantified, and that is used in calculation of the ASTM grain size number. So ASTM grain size number G, and the NA, that is the number of grains per unit square millimeter area, is determined in this method. Say there is a microstructure like this. So we draw one circle of the known diameter, and then we try to quantify that how many grains are there within the circle and how many grains are being intersected by the circle. So like say 1, 2, 3, 4, 5, like this, the grains within the circle are quantified, and then the grains being intersected by the circle are identified like this. So we have to simply count the number of grains within the circle or number of the grains which are being intersected by the circle. So say in this case, the 43 number of the grains are within the circle, which is taken as n1, and the 25 number of the grains are the circle. Say the circle area here is known is of the 0.5 square. So there is a very simple equation in calculating the in determining the number of the grains per unit area, is that the grains, number of grains which are within the circle will be counted as n1, and the number of grains which are being intersected by the circle at the circumference, they will be taken as n2, and then n2 divided by 2. So n1 taken as a full numbers of the grains, and n2 is taken as a half number. So n2 divided by the 2, sum of these two gives us the na. In addition to that, f, there is one factor which f which is multiplied, because if we change the magnification, then the number of the grains per unit area on the in the screen or on the paper can change significantly. So the f indicating the factor associated with the magnification is used. In this case, the 43 is the full number of the grains, and 25 number of grains being intersected divided by 2. So this is how we'll be having, like say, 55.5 number of the grains. These are the number of the grains in 0.5 square. Since we have to determine the number of grains per square so it will be doubled, because it is the 55.5 number of grains in half square area. So number of grains in 1 square area will be simply double here in this case. So it will be like 111 number of the grains per square So if we'll put then the 111 here, number of grains per square in this equation, then we'll get the value of the ASTM grain size number 3.8 after the calculation. So this is the simple method of determining the ASTM grain size number. Now, to take care of this f, we need to see little more details in the subsequent slides, and this is the equation which is used to calculate the ASTM grain size number. Now, in this method, as I have said, this method involves the drawing a circle of known diameter of the 5000 square on the photomicrograph or on the transparency placed on the projection screen. In this method, the magnification can be adjusted in such a way that at least the 50 number of grains are there in the test analysis or in the test area, and the count is made of the number of grains which are completely within the area, that is n, and the number of grains intersected by the test circle. That's what I have already explained. And NA is obtained from f, that is the factor, multiplying factor takes care of the magnification related thing, and this value of f is identified as per the magnification. Likewise, we can also use the rectangular area also for quantifying the grain size using the planimeter method. So when the rectangular shape is used, in that case a rectangle of the known area is encircled in the microstructure, and then we count the number of grains. The number of grains being intersected by these lines will be giving us n2. The number of grains within the rectangle will be giving us the n1. And to take care of the grains being intersected at these corners, the +1 is added. So here n1 plus n2 by 2 plus 1. So this 1 takes care of the number of grains being intersected. the 4 grains at the 4 corners, so the 1 is added. 1 accounts for the 4 corners grain interceptions, and F is the same, the Jeffreys multiplying factor. So there is a little modification in the equation of the Na when the test shape area is rectangular. Okay, and this is the equation. Once we have the value of Na, we can get the ASTM number G. So in this case, if we see 53 is the number of grains being completely within the rectangle, 43 number of the grains are being intercepted at rectangular lines. So half of that will be used, 53 plus 43 divided by 2 plus 1. That's how the average number of grains per unit area will be identified. So here when we use the different magnifications, the micrographs taken using the different magnifications, then the Jeffreys multiplying factor to obtain the number of grains per unit mm square is obtained by multiplying the value of F. So as per, like, if it is 1 magnification, means there is no magnification, so 0.002. If it is 100 magnification, then 2 is multiplied. If it is 500 magnification, then 50 is multiplied, and if it is 1000 magnification, then 200 is multiplied. So we have seen that Na is obtained through N1 plus N2 divided by 2. This is the case when the area is circular, and when we have the test area is rectangular, then N1 plus N2 divided by 2 plus 1. So this is the case when the test area is rectangular. So these are the two different equations used for determining the average number of grains per unit mm square using the planimetric method. Then we'll be talking about the intercept method. In intercept method, basically on the microstructure we try to draw the test lines of known length. Say this is the microstructure, so we'll be drawing the different lines vertically or horizontally, anything can be done, and then we will be counting number of interceptions of these lines with the grains or the grain boundaries. We can use both the number of grain interception or the grain boundary interceptions, and this method is particularly used to measure the kind of the anisotropy. So not just equexed but non-equexed grains can also be evaluated using this method. So just for an example, we'll take up this case where the microstructure, and here the 10 different test lines have been drawn like this. Okay, and these lines are of the standard length. Say test length line is 1000 micrometer. So these lines are drawn, and we'll try to see a particular line is being intercepted by how many grains, and those number of intercepts are counted. So say here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this we count. So say the line 1 is having the 20 number of intercepts. So if we quantify the average intercept length, so since the 20 number of interception by a line of 1000 micrometer, so average intercept length will be 50 micrometer. So let's say for this case it is 50 micrometer. Likewise, in the second line there are 26 number of intercepts. So the 1000 divided by 26. This will be giving us the 38.5. Another one, like say the 25 is the number of intercepts of the same length, but the number of intercepts are changing depending upon the size of the grains coming across. So 25 number intercepts means 1000 divided by 25. So this will be giving us 40. Likewise, we'll be counting the number of intercepts for each of these lines. Corresponding linear intercept length is calculated. Then just to come out with the average value of the intercept length, what we do, since we have used the 10 test lines and the average intercept length of each was different, so we can determine, just to average out the grain size, the average intercept length is determined. So sum of all these linear intercept length, this is divided by the 10 number of intercept lines. So average intercept length of all these measurements is say 43.8, and this average intercept length is used for calculating the ASTM grain size number. This L3 is the average intercept length, and using this equation we can get the value of the ASTM grain size number. So basically in this intercept method, we draw the straight line or circular line over the microstructure and then try to count the number of the intercepts of the grains or the grain boundaries. We can use any of these methods. So here this is the method when the intercept method has been explained using the circular lines. So here basically according to the ASTM, standard templates are available for circular lines of the known length. Say of the there are 3 lines of a total length of 500 mm, and those are placed over the microstructure. So to use this method, template or straight or curved lines of the known length are drawn over the photograph, and magnification of the micrograph is adjusted in such a way that all the grains or the grain boundaries are clearly visible. So we can count either the grain interceptions or the grain boundary interceptions. The number of the grains intercepted is represented by N, and when the number of grain boundary interception is counted, then it is represented by letter P. Both can be used. In case of the single phase structures, the grain boundary interceptions is preferred method, while in case of the multi-phase alloys, the grain interception, that's the N counting, helps in better way to get the average grain size using this method. So intercept method, a template of the straight or curved lines of known lengths are drawn on the microstructure, and then we try to count the interceptions of the grains or of the grain boundaries. If the grain boundary is tangent on the line, then it is counted as a half of the intersection, and if the triple point line junction is intersected, it is counted as 1.5 or 2. And test line is used in case when the circular line template is used and the magnification is adjusted in such a way that we get the 70 to 150 number of the intersections for better averaging. And when the grain intersections are counted, then we use N, and when the grain boundary intersections are counted, then it is counted as a P. And then we determine the grain interceptions per unit test length as NL, or the grain boundary interceptions per unit length as PL. And the methodology is simple. N is the say number of the grains counted for a given number of grain interceptions counted for a given test length, and then this N is divided by L test length line and magnification. So N is the number of the grain interception counted, L is the test length line, and M is the magnification. Okay, so this is similarly for grain boundary interceptions. P we count, then length of the test line divided by magnification. So this is used to calculate the PL, and this is used to calculate the NL. That is the number of grain interceptions per unit length or number of grain boundary interceptions per unit length. Say here the test line length is 500 mm of all these three circles, and the number of the grain boundary interceptions counted is say 75. We have to determine the PL first, that is the grain boundary interceptions per unit length. So to calculate that, 75 divided by 500 divided by 100. So this will be giving us the PL, that is the grain boundary interceptions per unit length. So from here we'll be getting 75 divided by 5, so 15, to determine the average intercept length. Average intercept length, and that is L3. L3 is obtained from the inverse of this NL or PL. So this L3 is basically average intercept length, and that is obtained from the inverse of PL or NL. So here, since we have taken the grain boundary interceptions, so that will be used for calculations. So L3 average intercept length will be obtained in this case inverse of the PL, which was 1 by 15. So this will be giving us the 0.066 value. So 0.067. So this L3 value is used in mm. This is used to calculate the ASTM number of the grain size. So when we'll put the L3 value in this equation 0.0067, then we get the ASTM grain size number 4.5. So this is just the methodology for single phase structure. Both NL and PL are same, and the NL, that is the grain boundary grain interceptions per unit length, or PL is the grain boundary interceptions per unit length. These are calculated using these simple equations as I have already explained. N is the number of the grain interceptions counted, and LT is the test length, and M is the magnification. Similarly, PL is the grain boundary interceptions per unit length, where P is the number of the grain boundary interceptions, and LT is the test length, and M is the magnification. And these will be giving us the value of L3, that is the mean intercept length. Mean intercept length is obtained from the inverse of either NL or PL as per the case which has been used for calculation of counting the grain interceptions or grain boundary intersections. And then when we put these this value of the L3 in this equation, we get the ASTM grain size number G value. So now let's summarize this presentation. In this presentation, basically, I've talked about the importance of the grain structure and the two methods of the grain size measurement. One was planimetric method and another was the intercept method. Thank you for your attention.